Yep. Hi, Jonathan.
Hi, Ahmed. Can you hear me?
I can hear you.
Perfect. Great.
Yep.
How are you?
Hello, everyone, and welcome to the Global Excel Bootcamp. And here we have Jonathan. And Jonathan is the co-founder at Wonderland, and he will be talking on increasing the scope of WebXR projects. So, Jonathan, you could do a quick introduction of yourself, and I'll take your screen up.
Perfect. Thank you. Thank you for the introduction, Hamid. Thank you for this opportunity to speak at the Global XR Bootcamp. This talk is obviously increasing the scope of WebXR projects. To make sure that you're in the right place and I'm not wasting your time, I'll give you a quick overview at the start, right? What is going to expect you in the next 40 minutes? I'm going to quickly start outlining our experience, where I come from, and why it might be valuable to listen to me. That's only 3 minutes or so I'm going to make it really quick. Since this is the Global XR Bootcamp and not the Global WebXR Bootcamp, I am going to introduce people to what is WebXR anyway and why you would use WebXR in the first place. For those who already know what WebXR is, bear with me. I'm going to make it short. It's going to be 5 minutes or something. But I think it's very important to pick up people that might not be familiar with the WebXR space already. The basis or foundation for this talk is going to be the WebXR challenges. So we have a lot of challenges when developing WebXR applications, and I'm going to outline those to then go into the biggest chunk of this talk, which is going to be increasing the scope of viable WebXR projects. So let's start talking about myself. We launched ConstructArcade over 2 years ago. It's a free VR browser games platform that hosts 24 games at the moment. It's the place to play and publish virtual reality games that run in the browser. While doing so, we had a lot of communication with a lot of different developers, and we came in touch with a lot of different frameworks to develop WebXR projects. We also developed our own games for this platform, and 2 of them you might know. Iron Rails and Barista Express are both featured in the Oculus browser. So if you have the Oculus Quest and you put it on and you clicked on the browser for the first time, then the new tab page actually lists Iron Rails and Barista Express in the recommended links. So that's how they grew to a little bit more popularity. Finally, we also did a lot of agency work where we especially worked with WebAR, a lot of A12 and ARJS, and also some large Aframe-based projects. Since January, we host the White Rabbit podcast, which is a WebXR-only podcast, so a pet podcast just about AR and VR on the web. You can find that on anchor.fm/whiterabbit. And we have 34 episodes, of which 9 are long guest episodes with important people in the WebXR space. All the knowledge, all the frustration, all the ideas we gained from the above are eventually led to the development of the Wonderland Engine about a year ago. So we've been developing Wonderland Engine for about 14 months. It's a WebXR-focused game engine. But what is WebXR anyway? And I thought I'd demonstrate this with a couple of examples. In this case, for AR, I'm showing this with 8th Wall. As you can see, it's just a browser running in a mobile phone, and it shows whatever your camera sees, but it overlays some 3D objects on top of it. And the nice thing about this is you just use some URL, in this case, a very short URL, and you can do tracking in 3D space on the camera, and then just overlay whatever augmented reality you want. So let's get back into the presentation here. For VR, I got some of our own examples. In this case, we're in the Oculus Quest, where we run the browser there, and by clicking Enter VR, we can then jump into a 3D experience and, for example, shoot magic balls, play games, but also do obviously useful educational, medical, and so on experiences as you are used to in XR. This, for example, is Iron Rails, a rail shooter that we also launched on Construct Arcade. And all of this is just running on websites. Barista Express is a simulation game where you have your own virtual cafe and serve espressos and latte macchiatos and cappuccinos to customers. So yeah, WebVR, therefore, is simply, and let's get this back to full screen, is simply VR and AR running in the browser. There's no installation needed, so it's basically web apps, but for VR. AR is done, for example, on mobile phones, but also in AR headsets. So, for example, on the HoloLens, for that, I recommend you watch Bringing Web-Based AR to HoloLens, which is Timmy Cook's talk, which will be in the second slot after the WebXR experts panel. VR, on the other hand, can be done through the Oculus Quest. Oculus Quest has a browser. Desktops obviously have browsers, so you can use any headset there, HTC Vive or Windows Mixed Reality, Oculus Rift, all of these. And so it runs on many other devices as well, because mobile VR also has browsers and so on. So how does this work? Browsers implement the so-called WebXR device API. That is a standard that allows your website to retrieve VR input. So the poses for the head and poses for controllers, or even the poses for augmented reality, which is, for example, which browsers use through ARCore or ARKit, and then give your website to use. If ARKit or ARCore is not available, you can still fall back to JavaScript libraries. For example, ARJS and AR Toolkit are very popular open source ones, and EighthWall is a more premium tracking solution for WebAR. And that's how you basically get the camera pose and know where to overlay 3D content. The actual 3D content, on the other hand, is done via WebGL. WebGL is an API that is also implemented by browsers to expose the GPU to your website. Why would I use all of this in the first place? Well, as you know, web apps have low friction, and it's the same with WebXR. It's an application that runs without download. It's really easy to get your users into your experience because they don't have to install anything through an app store or something. So the friction is really low. It's also, for the same reasons, it's fast to publish, because you just push your app to a web server and then share the link. There's no store curation or anything you need to wait for, or no qualities you need to fulfill. In this case, quality standards you need to fulfill. But generally, it's still super secure, because automatically the browser sandboxes it, which is really nice for getting it into corporations, getting your app into corporations, as there sometimes to install applications, you have to go to the IT department. And this allows you, obviously, to just share links with your coworkers, and they can try out your application. It's cross-platform, as the web is. Everything that runs a browser with WebXR support also supports your WebXR application. You don't have to write specific code for HTC Vive or Windows Mixed Reality. You can just target WebXR, and it should basically run everywhere. As we're on the web actually has a pretty nice mentality of being super fast to iterate. So if you make a change to your code, usually you have tools that just immediately reflect the changes in the browser, or after a couple of seconds. So it's really fast to iterate, fun to work with. In general, it's a great target for corporate projects, experiments, one-off apps, all this kind of stuff. There's no free lunch, though. WebXR comes with challenges, a lot of challenges, as we can see. The most important challenge is performance. The browser sandbox, which is an advantage in itself, also has a lot of overhead. To check your draw calls and everything, to check your code, make sure that it's actually safe and doesn't damage your the client, is very important. But it has it has a performance overhead there. JavaScript itself is not made to be high performance, so it has its overhead itself, and the garbage collection also makes it a little bit hard to control the performance, as you might get the garbage collection hitches every now and then. And we already have performance challenges, and now with VR, we have even more performance requirements, like solid and high frame rates to keep the user comfortable. And we need to render stereo at high resolution. Load time expectations are like, if users load your application on the web, it doesn't load like this, then people think it's broken. Even if you run on a toaster, which brings us to scalability, you might want to show a low resolution experience on said toaster to still be able to play it. But on high-end experiences, you might want to be able to provide a more high-end experience with more high-end assets, and generally a scaled-up experience. The skills to build WebXR apps, sadly, are very expensive. Not only do you need a JavaScript developer, but you need a JavaScript developer who also knows 3D graphics and computer graphics, knows about GPUs and this kinds of stuff. 3D asset creation has additional challenges, as not only do you need good performing assets, but also good performing assets that look good, right? So that the 3D artists need to know about optimization and to keep file sizes low and this kind of stuff. And finally, sadly, tooling is not up to the standards that native currently has. We don't have Unreal Engine or Unity in the way that we have on native, and that is actually something that we set out to do with Wonderland Engine. That's the challenge we solve, because usually tools solve all the above for you, but not so on WebXR currently. All of these challenges limit the scope of WebXR. So we want to increase the viable scope of WebXR projects. And in this talk, we're going to pick challenges and then propose the solution for them. So we pick each challenge I just listed, and we propose solutions for them. Let's start with performance. A question you might ask is, are GPUs slower on the web? No, of course not. It's just a lot harder to use the resources that we have with the GPU. And I'll show you in a minute why. And that is because of the browser sandbox. There's a solution to this, which is batching. And WebGL extensions like WebGL Multidraw help us implementing batching. And I'm going to go into greater detail about batching in a second. The JavaScript performance issue, on the other hand, can be solved, for example, by using WebAssembly or by using workers and threads. Also, details in a minute. So before I explain how batching works, I need to explain what a draw call is. See this scene, for example. You have the sphere, cone, and the cube, and now you need to make the CPU communicate to the GPU what it's supposed to do, right? You want it to draw the sphere, and you're gonna give it the shape of the sphere, the material of the sphere, which contains the color, and also how the light will bounce off the sphere and then produce the pixels you see above. And the GPU will then take that and actually produce pixels from that. If I draw this arrow here with the draw sphere above, then what I actually mean is kind of this, and this is still a rough oversimplification. The CPU, in this case, your website, issues the draw call, draw sphere, but then the browser will check the validity of this draw call and make sure that it doesn't crash the graphics driver or something. We don't want to do any harm to the client that accesses the website. It will then need to pass the boundary of the browser sandbox to get converted into a native graphics library call, for example, OpenGL, DirectX, and so on. This draw call will be used by the graphics driver, and then the GPU will actually do whatever it's supposed to. So just keep that in mind. If I have one line here that's actually, it has a lot of overhead. After we told the GPU, hey, draw this sphere, we'll go to draw cube and draw cone. Each of these arrows has this complexity. So we have a lot of overhead for every one of these. One big problem with this is that if you look at this cube, it's really simple, right? That's not a lot of work for the GPU. The GPU can chew through that, draw those pixels in basically no time. So what the CPU did, it told the GPU, draw this cube, and the GPU went like, hey, yeah, I'll do this, and did it, and then it just sits around, twiddles its thumb, because the CPU has so much overhead to figure out the next draw call that the GPU was like done ages ago and just waiting around. So batching now combines the draw calls to avoid the draw call overhead where possible. And that allows us to also use the GPU capacities way better. On a high level, it looks like this. You just say, draw the sphere and the cube and the cone. But in practice, this is a little bit more complicated. You can do it manually, like in Blender, for example. You can just select multiple objects, then right-click and join. Let's see this done. Join. And then they're batched together. Now they're only one draw call. But there is limitations to this. If you join these meshes, you need to fulfill the requirement of them having the same shader, the same material, the same texture, and that makes it a lot less flexible, right? The reason why all of these are gray and not the colors we had before is because they do have the same material now. If in Blender you have multiple materials, and you can obviously join objects with multiple materials, if one object has different materials, though, it'll still have different draw calls, because for the GPU to draw a mesh with multiple materials, it'll actually split it up into multiple meshes. So to fulfill the requirement of the same texture, we can actually build something called texture atlases. So that basically means we just put the textures together into one big texture and just make the UVs use specific areas in the texture. And that allows us to actually join a lot more objects by just using one texture atlas rather than 5 separate textures. Also, if we want to have dynamic objects, we require special shaders, because as you've seen in the GIF here before, once I join these, I only can move them all together. In Wonderland Engine, we do have special shaders, though. We join the meshes with a so-called object ID, which is just for every vertex, we have like a number that indicates, okay, this vertex came from the sphere, and this vertex came from the cone, and this vertex came from the cube. And that allows us to pass a list of materials and a list of transformations to the shaders, which then the shader can use and be like, okay, I got object ID 0. Let me look up 0 in the list of materials. Okay, that's this material, and list of transforms, and then know for this object ID, I need to put these vertices to a specific position. And that allows us to draw hundreds of dynamic objects in a single draw call, but dynamic objects. And that looks like this, for example. Here, it's a basic mesh particle system implemented only through the batching. There's no instancing here, in case you know what instancing is. This is just the batching, and every single one of these little particles, every single one of these meshes could be a totally different mesh. And that's the power of batching. This is one draw call. The object ID work does not need to be done if we have the WebGL multi-draw extension, because that allows us to pass a so-called draw ID to the shader, and we can just use that instead of the object ID for looking up our material list and our transformation lists. It also then allows us to do way more efficient optimizations on it, like culling and all sorts of other stuff. It's already supported in Chrome, and that also means it's supported in Oculus browser. So I think we did a lot of optimization on the GPU now. Let's move over to the CPU. And on the CPU, JavaScript was our main performance problem, right? WebAssembly is our solution for this. WebAssembly is a portable binary format, and that basically means it's it compiles in a way that, WebAssembly is basically a format that lists processor instructions, which the browser can more or less one-to-one convert to actual processor instructions, right? So it's an assembly language that gets converted to the processor instructions. It's not meant to be handwritten, just like assembly. You use it as a compile target. So you write your code in languages like C++, AssemblyScript, which is like a TypeScript derivative, Go or Rust, and you compile that and get WebAssembly out. WebAssembly is supposed to be up to 10 times faster than JavaScript. And I've seen a lot of numbers here. It's like it ranges from 2 to 30 times. So it obviously very much depends on what kind of code you have and what kind of use case. But generally, it is per default at least 2 times faster than your JavaScript. So if you don't want to use WebAssembly for some reason, both WebAssembly and JavaScript have a solution for multithreading or parallelization. Multithreading on the web allows us also to keep VR rendering going while we have long-running tasks. Imagine, for example, like a photo editing software for virtual reality, and now you put some long-running filter on it. You can't just stall the entire rendering process and like work through the filter and then just go back to the user and, hey, now I'm done. But instead, you would at least want to like show a loading screen or something, progress bar, I don't know. And multithreading allows you to do exactly that. You can just do 2 things at the same time. This also allows us to do cool stuff with like physics, because having physics run in parallel to our rendering code allows, for example, the physics simulation to run in a different frame rate, and therefore like doesn't stall our rendering stays smooth, and our user has a great experience. Talking about VR all the time, the VR comes with specific performance requirements. And here, luckily, it's not too much different from native optimization. And there's a lot of information on how to optimize for VR rendering. Just a couple of notes here. The Oculus Multiview 2 extension is basically a WebGL extension equivalent to the Multiview extensions that you have on native. So that allows you to avoid duplicating the draw calls for the left and the right eye. Instead, you do one draw call and it just automatically propagates to both eyes or both views. WebXR Layers is an extension to the WebXR spec that is hopefully coming very soon. And it will allow us, for example, to lower the refresh rates on 2D overlays. That means like 2D UIs often don't change for a while. So we can draw them once and then set that as a layer, and the layer will get updated with the head pose. But we don't have to continuously refresh that at 70 or 90 frames per second, right? WebXR Layers will allow us to do more efficient video decoding into like a 360-degree video layer, and it'll allow us to do things like fixed foveation. So lots of nice things coming there. Segueing into load time expectations without a segue. So obviously you want to keep your load times small, because with every second that your user spends time waiting on a web app, there's a chance that he'll just exit, and that's a bounce. First thing you'll have to look at to keep your load times low is to have a small runtime. So choose your engine wisely, because it's going to be completely loaded before the engine gets the chance to draw the first frame, right? And the first frame would, for example, be a loading screen. You can also do initial load optimizations, which means you only load the assets that you initially need. It doesn't make sense to load level 10 if you're currently in the menu, right? And similar. Loading screens tell the user, wait, my app is actually working. And finally, once you did all that, binary assets are a more efficient way to load after download. Okay, so binary assets like GLB might, for example, be faster than other formats like GLTF because they're smaller, but they're also actually faster to load for the JavaScript or WebAssembly runtime that you use. You might, for example, see if you open a GLTF file that it's all JSON. It's like it's all just text that says like it's a 0, a 1, a 3, and then commas in between and quotes, and all of this needs to be parsed at runtime. Your application needs to go through it and read all those characters and try to understand what it means for it, because it only uses binary, and the binary is what eventually will get passed to the GPU. So try to at least use GLB at minimum. GLB has the biggest portion of the data in binary already, and that can just be taken and shoved over to the GPU. It still has like a small JSON, so what you can do there is try to use a fully binary format, like Wonderland Engine does, for example, for runtime. To optimize your GLBs, once you have them, you can use Draco compression or quantization, for example. That's just two methods to get your sizes smaller of the GLBs, and I'll list some tools that are able to apply these optimizations for you in a very automatic way in like 2 or 3 slides. So finally, textures usually take up a very big portion of your application if you do a 3D WebXR application. And here, please at least use WebP. WebP is a very modern format, and it's actually supported on all browsers now with the, I think, latest release of Safari. So even on Mac and iOS, you can now use WebP, and it often is a lot smaller than JPEG or PNG. If you want to go all the way, though, please feel free to use Basis Universal. Basis Universal is a texture compression format that is not only smaller to download, because it has the size, for example, of a JPEG, but it's also smaller on the GPU. So a JPEG will be expanded to a completely raw image and then sent to the GPU, while Basis gets transcribed to a GPU format, which is also small on the GPU itself. The problem with the GPU formats is that many different devices support many different formats. And that's why we have Basis Universal in the first place, because Basis Universal is one format that we can so-called transcribe to the device-specific formats. So think of it this way. You have a PNG file or a JPEG file. You compress that using the Basis U tool. So just search for Basis Universal, you'll find it. And then you get a .basis file out. And at runtime, your application loads the .basis file and then transcribes it in a very efficient process to either ASTC on Android or PVRTC on iOS or BPTC on some desktop PCs that support it. And it could even fall back to RGBA for toasters. In Wonderland Engine, the editor compresses for you. So all your textures that you import with a GLB file or with any other scene assets, they automatically get compressed down to basis files, and the runtime will load them and transcribe them to whatever GPU formats are supported. We also allow packing all those in an atlas. Actually, we always pack them in an atlas because we need to for the batching. And packing GPU compressed textures into an atlas is like its own topic, because there's like limitations in WebGL and so on. But if there's one thing to finalize this load time expectations topic, optimize at package time, not at runtime. There's some applications, some frameworks load your file and then start optimizing that, resizing images to power of 2 and such. Try not doing that, because optimizing at runtime will increase the load time, especially on low-end devices. And with low-end devices, we found a segue to scalability on the web. Because it's so nice and portable, there will be many different devices accessing your content. And you will likely want to be able to provide a higher quality experience to the more powerful devices, while also tuning down the experience a bit for low-end mobile devices or similar. So what you can do there is obviously you can tweak the quality by device performance. That, for example, if you have a LOD system, you just tweak the LOD thresholds to like show a lower LOD longer when it's closer to you. You can also reduce all the texture resolutions or disable various effects. Maybe you have a bloom filter on desktop, but you disable that for mobile devices. Generally, though, you can download content by device performance using a different URL. So you have just two versions of the same mesh, for example, the same GLB file, scene file. And depending on how performant, how great the device is that is accessing it, the runtime should be deciding, okay, I'm going to download scene low or scene high, right? But for that, you obviously need someone who creates two versions of the same asset. And in WebXR, skills and work time is expensive. Why is that? WebXR development is expensive because there's a lot of code-based frameworks, and code-based frameworks need specialized code developers, right? Code writers. And so one solution you can have there is just to move to tools that require less code. That just broadens the skill pool you have there. You also need very highly optimized assets because not only do your assets need to look good, because you obviously want to have a high quality experience, but they also need to download fast and render fast. And artists who know this, how to do this, are more expensive than artists who don't, obviously. What you can do there is automate a lot of the optimization that allows you to use less well-optimized assets and just convert them into well-optimized assets. There's a lot of tools that can do this for you, so you're not alone there. With GLTF pipeline, that is open source. You can, for example, do the Draco compression that I talked about before. With Rapid Compact, you can do all sorts of things. You just upload the file and get an optimized file back that can be, I don't know, from 90 megabytes down to only 1 or something megabytes, and you can have like parameters how heavy you want to optimize it. And also there's, for example, Zux, I don't know how to pronounce that, mesh optimizer, also an open source project that Wonderland Engine is looking to implement or integrate that can optimize meshes for you, for example, by doing the quantization of the meshes. If you can't do any of that, or you did all of those, you are now with a fixed hourly rate for some developer, and now what you could do is reduce iteration times, right? That just reduces the expensive. You do less hours, have the same output, general efficiency goes up. And you would usually do that by moving to tools, native-like tools that have efficient workflows, right? Also moving to native-like tools creates bigger skill pools, because engines like Unreal Engine and Unity, they have huge skill pools. A lot of people know how to use these engines and know how to use these engines really well. We sadly don't have these tools on the web, though, because tooling is actually a very big problem of WebXR. Unity and Unreal Engine both have very big runtimes. They are insanely optimized for so many platforms, but the web is just so different from native platforms that they have not optimized it for the web. Unity Engine has a HTML5 target, but on mobile processors, for example, they have trouble because on WebGL, they don't support them. Unreal Engine, on the other hand, they outsource their HTML5 target to the community, and that means it has been stuck in 4.23 for I don't know how long now. On WebXR, however, we have many code-based frameworks. And code-based frameworks like Three.js and Babylon, for example, have a separate editor. And these don't do any optimization or usually don't do optimization and don't do asset processing, but at least they'll help kickstart your project by generating some source code for you. And instead of you hand placing by code with numbers objects in 3D space, you can actually have gizmos to modify and pull them in 3D space, which is way more. You just have more feedback doing so. There's also editors that do optimization and asset processing. For example, Play Canvas or Sumerian, AWS Sumerian. Those are both cloud-based frameworks, so they also run in your browser. So if you're into that, Wonderland Engine, on the other hand, made a very conscious decision not to be cloud-based, as we wanted a way tighter integration with the system. And to show you how that works, I prepared a video here. And I'm just going to talk over this because you don't get my audio here. On the top left, you see Wonderland Engine. You can move around with it with WASD and holding right mouse button. On the bottom right, you see the browser. If we click on the green arrow at the top there, Wonderland Engine will automatically open a new tab in our browser and load the packaged project in it. If we make a change in the editor, like moving this switch and then hit the hammer icon, it repackages and automatically reloads the browser. And we see the witch is indeed moved. If we make changes to component properties, like speeding up the WASD controls here a bit, then we can just repackage. It automatically reloads a couple of seconds after, and we see, oh, wow, we're really fast now. The rat seemed to behave a little unintentionally there, so let's see what's going on. We just change the speed to be a little bit slower and repackage. And we can tell, aha, okay, the mouse seems to be running backwards. To fix that, we could just invert the speed, but that's obviously not a very clean fix, as the speed is usually expected to be forward. But we at least see, okay, there's inversion happening, but it's probably a code issue. So let's find the JavaScript component, which is enemy.js here. We double-click it, and our system will open whatever we configured it to open JavaScript files with. In this case, my default here is NeoVim. And I can use this to find the incorrectly inverted speed here, remove the negation, and then save, which Wonderland Engine again will recognize and then automatically reload the browser for us with the updated JavaScript. And we see, aha, the mouse does indeed run forward. Can also make other changes, like setting the direction to always be forward. That requires us to disable the logic that decides where the rat is going. And if we save that again, aha, now the rat just moves forward. These properties that you see in the enemy component are actually generated from JavaScript. So you see the editor, code editor on the bottom right. If we add a new property called an object and make the type wl.type.object, if we save that a couple seconds after or split second after, it will actually generate a drop down here for us in which we can select a object for this property. If we add a float, it will generate a float input. And finally, we can do this with an enum value. An enum allows us to specify a list of possible values here. And the default should be value. And we see we have a drop down with like various strings that we specified. So we are trying to make the workflow really, really efficient here. I'd be super happy if you'd go try it out on wonderlandengine.com. You can sign up for a 30-day trial there. In addition to all of that, it implements many optimizations for you, so you don't need to worry about that. Let's see if I can get out of this. So, cool. So what does the future hold for WebXR? WebAssembly is a very recent technology, and it will continue to evolve. Threads has been added very recently, but SIMD will allow us to use special processor instructions that are really good at vector math, so 3D mathematics, which helps 3D game engines obviously a lot. or also just processing batches of data more efficiently, because they're implemented in hardware, and with WebAssembly, SIMD, we finally have access to them. WebGPU is the next API for web graphics. It's the future of web graphics, and probably will replace WebGL. It's a next-gen API like Vulkan, DirectX 12, and Metal, and it'll just, like those, give us more control over our GPU. It's more CPU-friendly because you do more work upfront instead of during the frame. And it finally brings us GPU compute, which, if you know WebGL, we don't have currently. So we cannot write compute shaders to use the GPU for non-graphics things. Generally, I think that WebXR and WebGPU, WebGL, WebAssembly are all moving slowly towards native performance. And we're really happy with Wonderland Engine to follow that evolution and evolve with it. Thank you so much for watching this talk and for your attention. We have, I think, about, still 10 minutes of Q&A left here. So looking forward to your questions.
Yep.
Hi, Hamid.
Lovely session. I mean, the part of the dynamic batching, that part was fantastic. I'm sure everyone have questions. So if you have questions, please do drop it in the comments section. But before we go to the question, like, what's your take on WebXR in the next 5 years? Where do you see WebXR going?
Connecting to what I said in the end, I think we're moving towards native performance. We're just recently started to get like the tools to be able to do great graphics on the web and to do high performance. We recently only got the tools to get WebVR input, right? To be able to do anything, or hand tracking. All these things are coming. And I think WebXR will very slowly move towards giving us all the possibilities that we can do on native, but comes with all the advantages that I talked about, the low friction or the easy deployment, generally the freedom of platform independence and all of that kind of stuff.
Great. So I'm just going to scroll through the comment section. So I think we have one here. So this.
Oh, hi, Roland. I know you. What about Aframe? Aframe does not do optimization for you. And while the HTML code is very easy to learn for a developer and even for non-developers, if you go to bigger projects, like, for example, we did with Barista Express, right? You start getting so many draw calls that Aframe actually has, it doesn't optimize that for you. And you'll hit the boundaries of WebGL there really quickly. We used a lot of Aframe in the past, and we also found, like, in addition to the draw call overhead, you get the overhead of the attributes, like the access to the DOM, right? I love Aframe, and it's super great for developers, but there's a lot of people who just want to build bigger projects, and I don't know, having an editor that does optimization for you and so on just saves a lot of time and allows bigger projects to be built.
Great. Also, this was also on my mind. Thanks, Alex. And this is it. So.
Thanks a lot. I hope WebGPU is fully supported on all browsers, not like some scripts. Talking to you, Chrome. Yeah, well, WebGPU is being implemented by Chrome, Firefox, and Safari, which is a huge win, because Safari initially didn't support WebGL 2, version 2, for a very long time. They actually started adding support for it very, very recently. It's already available in the Safari preview, technology preview, I think it's called. So hopefully, very soon, we'll have WebGL 2 on Safari. But they also are working with the group that is implementing WebGPU And I'm pretty sure that Chrome will support it too, and Edge is built on Chrome, and Oculus Browser is built on Chromium. So all of these, I'm pretty sure the Web GPU is going to be a great success there.
Great. I mean, I know that, I mean, one of the major challenges with WebXR currently is the compression. And I mean, I saw your slide, fantastic compression engine, but then, I mean, I still have to throw in Deepak question in, because I mean, I was also wondering about the .glb file. So
does Wonderland Engine optimize imported .glb? Can meshes be generated procedurally through scripting? So Wonderland, two parts of this question. Does Wonderland Engine optimize imported GLB? Yes, it does. If you import the GLB file, it will import the scene and then generate its own binary format from that. This binary format, for example, could have optimized meshes. It will automatically compress all the textures for you. And in the runtime, everything will be batched together, right? So depending on how your scene is created, nature the scene is, it might be 1 draw call, 2 draw calls, 10 draw calls, but usually not more for up to 1,000 objects, right? The second part of this question is, can meshes be generated procedurally through scripting? I assume this is also in Wonderland Engine. Yes, we have APIs to generate meshes through scripting, but we are early in development, so you're probably going to a very interesting edge there and might experience like some roughness there. But if you want to try doing that, feel free to hop on the Wonderland Engine Discord and talk about the questions you have there and get some help from us to get you through that.
Great. So I think we still have time for 1 or 2 more questions, but I'm just going to throw in my own question. So I mean, looking at the popularity of engines like Unity and Unreal Engine, and see the fact that most guys going to WebXR want to pass through WebGL from Unity, what's your comment? So if you're going to WebXR as a new developer, what tools do you recommend? Should the person go through Unity or through Wonderland?
That's a very great question. So for Unity and Unreal Engine developers, what do I recommend? How can they get into WebXR? We used a lot of Unreal Engine and also Unity in the past before we started on our WebXR trip. And when we started building WebXR apps, we found that there's nothing like Unity or Unreal Engine for WebXR, but Unity and Unreal Engine themselves, as I mentioned, have big runtimes. They're not well optimized for the web. So that's kind of why we built Wonderland Engine, right? But if you, for some reason, don't like Wonderland Engine, there's a special exporters for Unity, and Unity is currently working on Project Tiny, which will hopefully be a lot more suited also for the web, especially with low fidelity render pipelines. Sorry, I don't know the exact name. So hopefully that will evolve. There's also a Babylon.js exporter, which is also better than the main runtime, which does not support WebGL on mobile processors. But yeah, generally, I recommend we're trying to build a workflow that resembles something like Unity and Unreal Engine with Wonderland Engine. Feel free to check it out.
Great. Thank you, Jonathan. And just one last question. And so we have this.
That's a good question. Where can I get Wonderland Engine? Find it on wonderlandengine.com, and you can just go to the account on the top right, sign up there, and start a 30-day trial with the download. And yeah, happy to see you on the Wonderland Engine Discord.
Great. Thank you, Jonathan. I mean, I also would love to try out Wonderland. I'm trying it out after the stream. So
I'd be honored.
What's your Twitter? And I'm sure our audience would love to follow you on your social media pages.
I'm at Squarey on social media. That's SQUAREY. SQUAREY. it's going to be a little hard, but you'll probably find me as Jonathan Hale on LinkedIn, on definitely, probably also on Twitter by just searching Jonathan Hale. You'll find me through Wonderland Engine also. That way, the tweeting is across the channels. Yes.
Yep. And thank you, Jonathan. And after
Thank you
this,
so
we
much
have
as well.
the experts panel where you can throw direct questions to the WebXR experts. So hoping to see you all in
I'll
our
be
next episode.
part of that as well, even. So you can continue asking questions there. Thank you, everyone.